I have a call out to facilities. Maybe they can get it a little warmer in here by the end of class, but I don't know. All right. So the lengths of these bars represent two quantities. So I want you to estimate the relative size of the quantity represented by the blue bar relative to the quantity represented by the red bar. So what's the relative size of blue with respect to red? What's the relative size of blue with respect to red? Make an estimate. Go. Relative size of blue with respect to red. Relative size of the blue with respect to red. Okay, let's hear some ideas. So just, what did you think? Yeah.
Blue bar is 1.4 red bars.
He wants 1.4. Is that you're saying the relative size is 1.4?
Yeah.
Okay. Something different. What'd you think? Agree with that? Or something different?
We thought it was like 3 halves.
1.5.
Said like 5/3, so 1.6.
1.6. Greater than 1 for sure?
Yes.
Okay. Greater than 2?
No.
All right, so what if I told you that the quantity of the blue bar was 10 and the quantity of the red bar was 6? How would you find the relative size precisely?
10/6.
Two people are saying 10 over 6. Is it 10 over 6? What operation gives us relative size? Division, right? So your estimates were all good. 1.3, 1.4, 1.5. This is right in the ballpark. What is this, like 1.33?
Yeah.
1.33.
1.6.
No, 1.6. Sorry, 1.6. Okay. So using the idea of relative size, if I extended this out to 50, what would the red bar be? Now, using the, so if I extended the red bar out to 60, using relative size, how would you compute the quantity of the blue bar? Using relative size. So I'm not asking for an answer, I'm asking for an explanation of, if I extended the red bar out to 60, how would you use relative size to calculate the quantity of the blue bar?
You can make the 60 or 50? Because I think you said 50 the first time, and you just said 60.
No, I changed it when I said the red bar, I said 60. So I'm saying red bar to 60. So how would you use relative size to do the blue bar? Yeah?
Since we found the relative size relative red to the blue,
Okay.
and since we get the final length of the red bar, we just multiply that by the relative size factor.
So you're going to multiply what by what?
60, you multiply by 10 over 6.
You want 60 by 10 over 6.
Yeah, and it's kind of the same thing, but like we talked about last time, because relative size is by division. So 6 is 1/10 of 60, which is the relative size. So you would divide 10 by 1/10 to get the 100 unit length.
Is that using relative size?
No.
That's using the other thing, right? So you're saying, basically what you're saying is we're going to take this out times 10, right?
Yeah.
And therefore we're going to take this one out by 10. Is that relative size? Yeah, that's scaling factor. It's good, it's great reasoning, but it's not relative size reasoning. So relative size reasoning says that the blue one is always 10/6 of the red. So if the red is 60, then we want 10/6 of 60 to get the new quantity. That's relative size. 6 times 10 to get 60, and then therefore 10 times 10 to get the new size is scaling, right? That's scaling. Both are valid reasoning. Okay, so that's just a little review of last time. So let's kind of do a little big picture discussion here. Here's this term covariation. If you type covariation into Microsoft Word, you'll get a red line underneath it. It's not a real word, but it's a term that we kind of have invented, use. What do you suppose covariation means? What do you suppose covariation means? What?
When two quantities vary together.
Okay, when two quantities vary together. Yeah, right on the money. Okay, so when two quantities vary together. How do our topics thus far in the class relate to it? Have we done anything so far in the class that has to do with two quantities varying together? What's that? What'd you say before that, though?
Everything.
Yeah, everything, right? everything. Okay, and what does it have to do with calculus? Yeah.
Related rates.
Okay.
When like you're trying to calculate how fast something's changing in comparison to the other.
Yeah, so rate of change. So rate of change, how fast one thing changes relative, one quantity changes relative to another. So the answer again is everything. This is kind of the forum for calculus, is this thing called covariation, two quantities varying together. So remember we talked on the first day about that all the ideas are going to come in groups, that we have coherence to everything we're doing. So everything that I'm choosing to do is all about building up this idea of covariation, which is kind of the forum or the environment in which we do calculus. So how two quantities change together. So we started with multiplication division. So these are the basic operations about that represent quantities, changing quantities in measurement. So far we saw multiplication was scaling, right? Scaling quantities, division, relative size. Okay, and so we've talked about visual representations. We've done the bars. And then last time we talked about the graphs that you're more familiar with, right? The standard graph, x and y axes. And we kind of talked about what those really mean by relating them to the horizontal bars. Okay, and then we're going to move on today to, so that's visual representation of covariation, some kind of a visual. And so, but then equally important is understanding symbolic representations of covariation, and that is function notation. That's what we'll do today. So everything we're on a journey. It's all tying together, okay? Everything we do for a purpose. And that purpose is really coming to understand how calculus models how two quantities change together. So you've all seen, in your past math experience, you've all seen something like this before, right? What's this called? X-axis, y-axis, and then we have this curve. Okay? So the question is, thinking back from Friday, what is represented by this curve in a very general sense? In a very general sense, what are you looking at when you look at a curve in the xy plane? Talk to your partner. Okay, let's hear your ideas here. Volunteer. So what, when you're looking at this curve here, what is this curve representing? Somebody new. I don't have my, once I get the roll up, I'll just start calling. Yes?
Collection of points.
Collection of points. Say more.
Every output for X.
Every output for X. Okay. How is it showing how is it showing points, or how is it showing every output for X? In the back, yeah. Okay, the covariation between two quantities. Okay. How does it do that? Yeah, this is all right. Everything you're saying is correct.
It represents a function, so you could put x values into the function and that will give you the outputs.
Okay. So tie it all together. Everything's being said is true. So
The curve is going through.
what's that?
Like the curve is just going through all the points that were plotted.
Okay, all the points that were plotted.
Every point up into what X what or what.
Okay. Other ideas? All correct. What you guys are saying. How about this? What does a visualization like this, how does it relate to a visualization like that? Yes, ma'am.
So every y point is relative to every x point.
Okay. Every y point is relative to every x point. Okay. Any other volunteers? Nicole?
Lines represent like the distance from the x and y axis.
Okay.
So that'd be the distance from 0.
Distance from 0. Okay.
It represents maybe the scaling factor between two bars at all, like all points.
Scaling factors at all times. Okay, so what does, how does the illustration on the left show the same thing as the illustration on the right? Talk to your partner. So how does the illustration on the left shows the exact same story as this right here? Where's Judith?
Every time.
Oh, did I already pick you already?
A couple days ago, but
Okay.
it's okay.
All right.
We said it's like the collection of points that shows the relationship between x and y.
The collection of points that shows the relationship between x and y. Okay? Other ideas?
The red bar kind of represents like the distance from 0, and then the blue bar kind of represents all the y values, the distance from the
Okay, the red bar represents the distance from 0, and the blue bar represents
all the y.
all the y coordinates. Lauren in the back.
If we were to type blue on 90 degrees
Okay?
and put it at the end of the red line,
If we were to take the blue and turn it 90 degrees and put it on the red end of the red line, it would create this. Is that what you're saying?
Top part of the blue bar.
What does the red bar represent? The x quantity, right? The value of the x quantity. What does the blue bar represent? Y. Okay.
And relative to
Okay, I'm glad I did that. So I'm just making smaller, okay? So all I did was, it's the same illustration. All I did was, let's see, maybe I do need to zoom in. Yeah, there we go. Yeah. It's the same, they're varying the same together. It just flipped the blue bar onto the end of the red bar. Remember we said, what if we put a plane? What if we put a plane on the top of the blue bar and then tracked its vapor trail? What's the result? Exact same thing, right? Exact same thing. So this is, what is this? This is a record. It's a record of how the x quantity and the y quantity are changing together, right? And how is it a record of that? It's every single point. So you said that. It's every single point such that you have the x quantity and the corresponding y quantity. And when we graph every single point, it would take a long time to graph every single point, right? So this is our kind of efficient way of showing all the points, all the individual points. So when you look at any graph from here on out, your image should be, that's just a bunch of points. How many points? Infinite number of points. An infinite number of points. And each one of those points is a x quantity and a corresponding y quantity put up 90 degrees to it.
Wouldn't it be X number of points?
What's that?
Wouldn't it be X number of points as long as it passes the vertical line test?
X number of points. Oops.
Since it never goes back on itself, there will only be, every.
So from 0 to 2, you're saying there's 2 points? That's what you're saying.
It's
X.
divided infinitely. So.
Yeah, there's an infinite number of points, right? If it's a continuous variable, it'll be an infinite number of points. Okay. So the horizontal blue bars and then the graph, they're really two different ways of showing the same thing. How the two quantities change together. All right, so we had our example from last time. Let's return to that. And that was that our x quantity represented So let's turn the graph axes on. So what was our, we had our x quantity was I think I said it was volume of water in a bottle in milliliters, did we say? And Y was the height of the water in centimeters. Okay, and what was the relationship, do you remember, between X and Y? In other words, what's the relative size of Y with respect to X? Do you remember what we had? We said that that blue bar was always 1/4 the length of the red bar. So given a volume that we put in, the height was 1/4. As a number, it was 1/4 of whatever that volume in milliliters that we put in centimeters. Okay, so we talked about how function notation is the symbolic representation of how two quantities change together. So this is the graph representation. So function notation looks like this. So we could say f of x. So x is the input, and the input is the independent variable. It's the one we're free to choose whatever we want it to be. Okay? So we're free to choose to put 5 milliliters in the bottle, or 2 milliliters, or half a milliliter. There's nothing constraining us. So that's called the input or the independent variable. Then the whole notation together, this whole thing then, represents the output. Okay? F, just the letter F, that's the name of the function. So the name is whatever we choose there. The input goes in the parentheses, and the whole notation, that whole thing, it's not F times X, right? That whole thing together represents the output of the function when the input is X. And then what we have is the rule that tells us how to get the output given the input. So this is called the rule. So those are the elements of a function. The input quantity, the output quantity, the name, and the rule. So what I want you to do is I want you to interpret. I'm not asking you to do a calculation and crank out an answer. I'm asking you to interpret the meanings of these expressions. Let me put one more in there. So this is, say, number 1, number 2. How about this? FFC. It's number 3, 4. So I'm asking you in each case to interpret the meanings of those expressions. So it's like you can just verbalize it, or in your notes write a sentence. What do each of those mean? Okay, so you can work with your partner. Take a couple minutes. Interpret or write a sentence or verbally explain what each of those notations mean. Go. Oh, sorry. Your answer should always be in terms of the quantities. So make all your answers in terms of volume and height. All your answers should be in terms of volume and height.
There are
Okay, so don't start this till I tell you. Work on this, okay? Work on
there is
this.
some number A, right? There is some number A. Value is it's a value. The water. The wall. F of A is the height. So I guess you'd say Y value or height.
Just grab one and put it to the side. And work on this.
The height of the water is 0.7.
Yeah, it would be the height of the water, 7, the volume.
No, because this is X value, so that's how many milliliters of water in there. This is the height. This entire thing is the height, just that alone is what's actually in the bottle. For F, so there is some value B plus 3 milliliters.
The height of the water, the volume equals
F of 7. So this is actually the
All right, where's Jatia? How'd you do on number 1? Can you explain what F of 2 is?
I said the height in milliliters and the volume in centimeters.
She said the height in centimeters?
Yes, and the height in centimeters and volume in 2 milliliters.
The height in centimeters when the volume is 2 milliliters. What do you think? Perfect. That's exactly what it is. That whole thing represents an output. It represents a height in centimeters, specifically when the volume is 2. Add it in. Okay? And what is the value of that? It's a value. What's the value of that? What is that height in centimeters? 1/2, right? It's 1/2, which you can find by using the rule. Okay, what about F of A? Where's Christina Zambrano? Tell me, F of A, what does that stand for?
So the volume of water is A, and the height is going to be 1/4 of A.
Okay, that's true. So that she said that the volume is A, and then the height is 1/4 of A. But what does that expression mean? What is it?
Comparison between the two.
Nope. It's one of the two things you said. So you said you said a volume and a height. But it's that thing right there is one of those two things.
Oh, would it be the height?
Would it be the height?
The outside?
It's the height. Which height is it? When the volume in the bottle is A. So this thing is the height when the volume is A. Okay, number 3. Where's Daniel Schleicher? Yes, sir.
Number 3 is telling you that the volume, that the height of the water is 0.7 centimeters at C milliliters volume.
What do you think? Yeah, that's right. He said it's telling you that the height is 0.7 when the volume in milliliters added is C. That's what you said, right? Yep. Good. Okay. Number 4, volunteer. Yes, sir. Helios, right? Ah, got it.
The height of the water when the volume is 7
Okay.
minus the height of water when the volume is 2.
Absolutely correct. But we want to now say, isn't that's just one number though, right? When we do that calculation, we're going to get one value. So what is that one value? What's the interpretation of that one value? What's the name again?
Tyler?
Tyler.
It's going to be the difference in height at volume of 7 and from the height in volume of 2.
And what is that? So that it's still saying, you're still kind of saying this minus this by saying difference. So what is the difference? The change in height, right? The change in height. Go ahead.
As the volume changes from 7 to 2.
Try again.
Oh yeah, 2 to 7.
Right. It's going to be the change in height that we see in the bottle as the volume changes from starting at 2, ending at 7. Right? So that whole quantity is going to be a change in height. Remember subtraction from your reading? Subtraction represents change. And so this will be the change when the volume starts at 2 and ends up at 7. That'll give you the change in height. Okay? In its meaning, is it the same as f of 5? So whether or not the value in this case is the same. Could we just say it has the same meaning as f of 5? Could we say that?
No.
So you shook your head in the black shirt. Tell them your name. Yeah. Stephanie? So you shook your head. Why not?
I'm not exactly sure why, but that seems a little bit too simple.
Well, tell me what the meaning of that is. What is the meaning of f of 5?
It's the height in centimeters when the volume is 5.
Okay, and what was this again?
It was the change in height as the bottle changed from 2 milliliters to 7 milliliters.
They're just totally different, right? They're two totally different things. She said it perfectly. This is the height when the volume in the bottle is 5. This is a change in height from when we start with 2 and end at 7. Totally different meanings. But calculus students throughout the ages have tried to say that this is the same as this. Okay? Now, in certain situations, those values may turn out to be the same, but the meanings are totally different. Do you see? Okay, how about this last one? F of b plus 3. Somebody new hasn't spoken up yet. Volunteer. DJ.
The height of the water in centimeters when 3 milliliters is added to the original B volume.
Okay, so she's saying original B volume, and you added 3 centimeters, and you get
Or
3
3 milliliters.
milliliters.
You get like height of the water in centimeters.
Height of the water in centimeters. It's the height of the water in centimeters when how much water is in there? B plus 3 milliliters. B plus 3 milliliters. Any questions on... So functions, use the function notation, which is the symbolic representation of our covariation. It's absolutely imperative, and we have it all through calculus. You've seen it before. It's going to be all in calculus. So we have to really be able to look at these types of notations and expressions and just know what those meanings are. So you got lots of practice on your worksheet. Start with page 1, which is the swimming pool example. A equals P of W. A equals P of W. You can work together. Take your time. Make sure you really are understanding each one. And then we can walk around and field questions. Okay? Not at all. Totally fine. Okay.
They'll be done on Wednesday.
That's great. I just was gonna, if you had them, I was gonna hand them back now, but. Jacob, right here. Kaiser. Colin. Colin Barnabas. Not here. Olivia's here. Hui Chen. I don't think she's come yet, so we can maybe administratively drop her. Autumn's here. Peter Cologne. How are you? Tyler. Adonijah. Julie. Samantha. Hai. It's right here. Chen Rui. Right there. Daniel Herder. That's Daniel Herder, okay? Anthony Ignacio. Elizabeth Judd, right here in the front. Tyler King, right there. Hang Koo. David Lee. You got everyone except Chen Hui so far, I think. DJ. He's here. That's Dwayne. He goes by DJ. C. Lee is here. Andrew. Yep. Stanley Lubansky. Ziu. Rohit. Rohit Manis. Not here. Nicole. Richard Martin. Yep. Katie Massey. She's here. Kobe must be new. He must be new. Megan McCrea. Marcus. Judith is here. Andrew Myers. Adelaide. New Maine. Helios. Got it that time. Shinzi. Savannah. Lauren is here. Tatia is here. Chelsea's in the back. Lauren's in the back. Cindy's right here in front. Stephanie is in the back. Daniel Sleitcher is in the back. Amos. Connor Simpson. Christopher. Daniel St. Germain is over here. Joshua is right here in front. You go by Josh? Do you go by Josh or Joshua? Either's fine. Okay. Corey's right here in front. Christina Trin. She's here. Lionel So. Wanting Wang. Z Wang. Tylea. Sharon Wu. Christina Zambrano is here. And Eric. Eric Zoe. You go by Eric, right? Yeah. So just two? Two or three? How many were there?
I have Ivan S.
What's that?
I have Ivan S. This was as of yesterday.
Yeah, okay. Yeah, Ivan's gone.
Okay. Thank you.
Thank you.
basically saying, when water height is
Okay, questions? Okay, so, yeah, those are both, oh, I'm asking which quantity is this thing, but I'm asking what the quantity. So you're giving me representations of quantity, which are both valid, you're right, PW or A, but what is the quantity? It's the characteristic, that's the output, what is it?
It's the height of water.
No. That's the output, that's what A equals.
A equals the area.
Area.
Oh, okay.
So you asked me, is it PW or A? Well, either one. Well, what quantity is that? What quantity is A? Or PW? Yeah. The area of the water.
Just decide one. Mark?
Yeah.
We just decide one.
No, can you keep going?
So T is.
On the second page, number 6, just stop reading for a second. On the second page, number 6, it should be referring to number 5, not number 2. Cross out number 2 and put number 5. Right on that. Number 6 is number 5.
What I heard numbers, but I was going to say is that when absolute quantity, it actually has what exactly it is, not just the variable. Yeah, then it's T of T. So this takes travel by the car. At T seconds. See what should we represent D? Oh, no, D equals G of T. D equals G of T. Well, this wouldn't technically be D of T because it's G is like the output name, but it has to be a function of T. Yeah, I know, but it's D as a function of T. Like it's without D, so if it equals D, that means that the function has to have a name that you plug T into, and in this case it's G, but it doesn't tell you that. It's just you need to talk about the quantity. Huh? Oh, not in this part.
And number 5 it does that.
Yeah.
So how to explain? What do you think of this?
It's the surface area given A plus 1. Considering the difference between the area and the volume, with the water height of 1.
Yeah, so if you were to calculate that, you'd get a single quantity, right? You'd get a single value. So what does that single value mean? Rather than explaining it as this minus this, we want to explain it as one unit, one thing. What one thing is it?
It's the change
Change in
the area of the water. Surface area of the water.
Which change? Okay, so that's right. It's a change in surface area.
How do I say this?
Yeah.
Saying minus.
No, it's a change. Okay, it's a change, and so change from is going to be the change from some starting water height to some other's water height, right? So what's the starting water height and what's the final water height? One second. Let's think about this. So f of 2 is 1/2. F of 7 is, how's that? No. 2 is 7/4.
So let's think about it from this one, right? This G right here.
Well, it would be
So-
G of 6 minus G of 0.
The
How do you
height-
put G of 0?
Just
I mean, because it doesn't say
So
that
think
it's,
about where.
like if you're just saying.
So that number 5/4 is the change in water height
I mean, I guess you would
when
say
what?
that G of 0, because if it's like, what if it's like G of 0 equals G of X equals X plus 2.
Just
Then
the y dot
starting distance of 2.
would, is that a single value?
When-
It's not so make it make
Are
distance.
there,
You gotta think about it, huh?
there's multiple x values.
Ask the question again.
So we're asking, what does this represent right here?
If I give you an x value,
It represents the change in the height of the water.
Change in the height of the water.
Considering the change in the volume.
From what to what? What's the starting volume and the final volume?
What's the the starting volume. That's not taking two volumes and then putting them together.
So consider this. You get negative 5/4. So in one case you get 5/4. In the other case you get negative 5/4. So what does the height changing 5/4 mean? The height is going which way? Up. So how does the height go up? Starting with how much volume to how much? So this is the starting volume,
Because I was gonna write 7 plus X.
right? Does that help? Because if you switch it the other way, what's the height doing?
It's going down.
Going down. So your starting volume is?
Be
7 is the starting volume, 2 is the,
Would you say that's the function of 7?
what's that?
Would you word it like the function of
F of 7.
F of 7?
F of 7. F of 7.
yeah, so let's.
Does that help with your question now?
I'm wondering how I word it when it comes to.
So it's the change in, change in,
I'm going to write the change of the height of area of the water.
change.
The height of the water to find the area, right?
That's the whole, our whole point of our conversation was
What do I need to-
starting at what height and going to what height. So starting at what height?
Start at P1.
W is not.
Not starting at P of 1. P of 1 is not a height.
That's just how my brain
So
would.
W is.
P of 1 is the output.
The area is dependent.
Starting
on-
at P1 meter.
Starting at height of 1, right?
That's what 1 meter,
Yeah, no,
change
it's-
of
but you need to think it through. to figure out.
8 meters plus 1.
So,
Not a change of A plus 1.
I'm not knowing how to word it correctly.
I know, I just.
Well, if you knew what it was doing, you'd be able to word it correctly. So you just have to think about it. So you got a pool, right?
No, you helped me. So. This.
And we're finding the change in area for some change in height, right? So what's the height here? And what's the height here? And what's the change in height?
This function represents the change of height, right?
Does it? No, it doesn't.
Represents the change of the surface area.
Change the surface area. Change the surface area. Okay. Which change of surface area is it? Okay, so we have like a minute, just a minute left. Is there a request from page 1, the pool problem? One you want me to talk about? What's that? 3B. 3B is telling you that the area of the water surface is 14.3 meters squared at a height of X. Does it make sense? Okay. Nicole?
E or F?
E or F? Alright, pick one. E. So E, that's the change in water surface area when the height of the water starts at 1 and changes by A. Did you catch it? It's the change in the water surface area when the height of the water starts at 1 and goes up how much?
A plus
A.
1.
No, it goes up A. So that its final height is 1 plus A, right? Starting at 1, it's going to go up A, so its final height is 1 plus A. Make sense? Okay, what I want you to do for Wednesday is go ahead and finish this, and we'll include it with Wednesday's homework, which is online. So for Wednesday's homework, there will be a problem-solving element to it. I didn't do a problem exactly like that, but you have all the elements that you need to solve it. What it's based on is the fact that when you take a picture, there's something called shutter speed. And the shutter speed is that the shutter opens, it doesn't open for just an instant. It opens for an interval of time and lets all the light in over an interval of time. Okay? So there's a time when that shutter opens, and then a little bit later, the shutter closes. There's an interval there. And so the shutter speed is that amount of time. Does it make sense? And that's what you're going to need, that idea is what you're going to need to solve. Okay? Now the office hours if you need help.
Hey, sir, I wasn't here last week because I was on military orders.
1 second. Let me turn this off. Hold on 1 second.